Okay, so now we move on to the primer on probability distribution part 2. So this is a continuation of what we covered in part 1. So let's start with one of the most important distributions, which is the normal distribution. So this was developed by Gauss, and in some cases it is also known as the Gaussian distribution, in which a variable can take any value within a range and the probability distribution is continuous. So, how does the normal distribution look like? It's symmetrical around the vertical line, which is the mean, and it is bell shaped. Both the left and the right hand tails extend indefinitely, and the median and the mode are also at the center. So, at for a normal distribution, the mean, median, and mode have the same value, and typically it is the mean is denoted by mu, and standard deviation is denoted by sigma, the Greek letters for the two parameters which define a normal distribution. Now, normal distribution can look like what we've given over here on this chart. It can be extremely peaked, like what the blue distribution looks like, which has a low standard deviation, or it could be plateaued, like what the brown distribution looks like with a standard deviation of 5, or it could be somewhere in between, like the red distribution, which has a standard distribution of 1. Now, one thing to keep in mind, which is important, is that about 68% of the values lie within 1, plus 1, and minus 1 standard deviation. 95.5% lie within plus minus 2 standard deviations, and 99.7 within plus minus 3 standard deviation. And the total area under the normal curve is 1. Now, how do you calculate the values within a normal distribution? And one of the important concepts you need to understand is what we call as a z-score. So, if x is a variable which is normally distributed, it can be denoted, x can be denoted as n mu comma sigma, where mu is the mean and sigma is the standard deviation, and the z score is calculated as x minus mu over sigma. So what does it tell you? It tells you how many standard deviations the value of x is above, which means it is to the right of, or below, which means it is to the left of the mean, which is mu. So values which are larger than the mean have a positive z score, and values of x which have a smaller than mean have a negative z score. And if it's equal to the mean, then x has a z score value of 0. So if you have a mean of 100 and standard deviation of 35, so within one standard deviation, you will have between 100 and 135 respectively. So you can also calculate it for 2 and 3 standard deviations as well to understand what the range would be. So let's take an example of how we use this normal distribution. So X has a normal distribution with a mean mu 50 and standard deviation sigma of 6. So from the earlier side, we know that about 68% of the values lie within plus minus 1 standard deviation. So 68% of the x values will lie between minus 6 and plus 6 standard deviation, because sigma value is 6. So value of 50 minus 6, which is 44, and 50 plus 6, 56, are within one standard deviation, which is basically mu minus sigma and mu plus sigma. So the z scores are minus 1 and plus 1 respectively for 44 and 56. And how do you get this minus 1 plus 1 from the earlier formula? Z is nothing but x minus mu over sigma. So you plug in the values of x, mu, and sigma, so you'll get -1 and +1 respectively. Likewise, about 95% will lie between two standard deviations. So which means -2 into 6, which is -12 to +12. So the range of values would be 38 to 62 within two standard deviations from the mean. So z scores are -2 and +2 for 38 and 52 respectively. So you can calculate it by plugging it into the formula. So suppose x has a normal distribution with a mean of 5 and standard deviation of 6. And suppose x is equal to 17, then z is equal to 17 minus 5, which is the mean, divided by 6, which is 2. And what does this mean? It means that x having a value of 17 is two standard deviations above or to the right of the mean, which is 5. Suppose x is equal to 1, then z is equal to 1 minus 5 by 6, which is minus 0.67, which means that x equal to 1 is 0.67 standard deviations below or to the left of the mean equal to 5. So let's take an example. You have a final exam score in a statistics class, which are normally distributed with a mean of 63 and standard deviation of 5. So find the probability that a randomly selected student scored more than 65 and randomly selected student scored less than 85. So what does the distribution look like? So x tends to normal distribution, mean of 63 and standard deviation of 5, which is what is given to us in this problem. So what you have to do for the first section, you have to find probability of x greater than 65. So Z1 value will be x minus mu over sigma, which is 65 minus 63 by 5, which is zero point 0.4. So 65 is zero point 0.4 standard deviations to the right of the mean, which is 63. Now, you can calculate the cumulative probability up to Z1, which is zero point 0.4, is 0.6554. Now you can do this either by looking at the normal table or you can use an Excel function, norm dist, which is within parentheses 65, which is the x value, comma 63, the mean, comma 5, which is the standard deviation, and 1 is the default value. So it gives you 0.6554. So 1 minus 6.6554, which is 0.3446, is the probability that you have a person, randomly selected student, who will have a score of more than 65, because the area under the curve is 1. Now, what is the probability that a randomly selected student scored less than 85? Now, that is something which you can try out also, but I'll quickly run through it. So 85 means 85 minus 63, which is the mean, by 5, which is 4.4. So 85 is 4.4 standard deviations to the right of the mean. Using earlier formula, non-dist, you find which is equal to almost 1. So there is probability of one student scoring less than 85 is only 1, which means almost all the students have scored 85 or below. So this is another example also which you can run through. It's pretty much similar to what I've covered in the earlier sheets as well. And this will give you a flavor of how to do the calculation. So that's pretty much on the normal distribution. Thanks.